So problem number 6 from the review is a rational function that has lots of different pieces and parts to it. Now we're going to go down the list and just do A through H and analyze everything we can. Now I have written on the top here the first and the second derivative, and so the first and the second derivative, trying to see where I had actually done the work. Here it is. Here is some of the work if you did want to see where I came up with those derivatives. But remember, for these, you're going to want to use the quotient rule. Look at some of the patterns that we see here. The original had an x squared minus 1 in the denominator. The first derivative, that power went up by 1, and then the second derivative, that power went up by 1 more. And they should reduce that way every time for fractional functions, or at least many times you'll see that pattern. Okay. So let's take a look here at problem number 6. So I have the derivatives there. First off, let's talk about the holes and the vertical asymptotes. Holes only occur if there is a factor in the top that matches a factor in the bottom. I'm not worried about an example with holes. This example does have a vertical asymptote. If we take a look at the bottom, you're going to set the bottom equal to 0, and you're going to solve it. Usually factoring is a good way to go, but this one you could have solved a little differently. And so we get vertical asymptotes at plus or minus 1. Okay? Now, the domain is essentially linked to the holes in the vertical asymptotes. So remember, if there are holes in vertical asymptotes, you need to remove those from the domain. And so our domain here goes from negative infinity up to negative 1, jumps across that asymptote to positive 1, and can keep going after the asymptote on the other side. Now remember what this tells us. This tells us that our graph is in 3 unique pieces, so that's very helpful, okay? Now let's take a look at our intercepts. The x-intercept is where the top of our function equals 0, because a rational function will only equal 0 where the top is equal to 0. So 2x squared equals 0 when x is 0. Now the y-intercept, you are going to physically plug in 0. So if we plug in 0, we get 0 over negative 1 or 0. So the only intercept for this, for both the x and the y intercepts, are 0, 0. We just hit 0, 0. We don't hit the x or y axis any other places. So just keep that in mind when you are graphing. So now let's talk about horizontal asymptotes. For a horizontal asymptote, we are talking about looking at the comparison of the top and bottom. You'll notice right now we have used the original function for A, B, C, and D. Okay, and we're going to use the original function for E. So these are all based upon the original function. Now, horizontal asymptotes, remember you look at the lead term of the top and the lead term of the bottom. If the bottom has a higher lead term, we are going to have a horizontal asymptote of 0. But in this case, our lead term on top has a square, and a lead term on the bottom also has a square. So instead, that's the time where we use those coefficients. The coefficient on top is 2. The coefficient on the bottom is 1. That's where we got 2 over 1, or 2, for our horizontal asymptotes. Let's talk about symmetry. Symmetry is about 2 things. I want you to check 2 things for symmetry. If you plug in negative x and it goes back to the original form, it is even with y-axis symmetry. If you plug in negative x and it is the opposite of your original form, then it is odd with origin symmetry. So that's really what we're checking. Now, if we plug in negative x into our original function, what happens here is the negative x is inside a square in both places. So when that happens, they go right back to where they started. So that's the original. If it's the original, then it is even with y-axis symmetry. So now we know it is even with y-axis symmetry. Okay? So you'll notice A through E, you're using the original form of our function. Now, let's take a look at part F. Part F, we have to use the first derivative for everything related to increasing, decreasing, and maxes and mins. Now, here's the first derivative. Let's go ahead and use it to make our plus and minus chart. Now, one of the mistakes that is commonly made is you must include all factors of the top and all factors of the bottom, including the squares. So keep that in mind. Now, if I put the first derivative in factored form, I technically get x plus 1 squared and x minus 1 squared because this factors to be x plus 1, x minus 1, and there's a square on it, so I actually have 2 of each. Now, do you have to break it apart? No. Do you need to break it apart to find the critical numbers? Yes. Now, the critical numbers, remember, are the zeros of the top and the zeros of the bottom. So our critical numbers here, the top gives us a critical number of 0. The bottom, we already know, gives us a critical number of plus or minus 1. So we're going to make our first derivative chart using -1, 0, and +1. Now, what you're going to do here is you're going to use open circles for the -1 and +1 because they came from the bottom. The bottom points where the bottom equals 0 of a fraction is undefined. But the critical number of 0 is a critical number. It's a number that works. I can have 0 in the top of my function, just not in the bottom of my function. So I colored that in to remind me of that, so I know that something might happen at 0. Now remember, if you go back and look at our domain, we have 3 pieces. We have a piece over here, we have a piece in here, we have a piece over here. So it makes sense that we should have open circles in those 2 locations. Okay. Now along the side here, I'm going to list out my factors to make my plus minus chart. Now you can do it a quick way. You can just write -4x. You can also write each one of these separated, or you can just write the whole thing, x squared minus 1 squared, as long as you include everything. Okay, so let's plug in some values. So let's plug in -2, -1/2, +1/2, and 2. If we plug in -2, so I'm just going to go down the list. If I plug -2 into the top, -4 times -2 is a positive. This is always positive because it's going to get squared, and so that's a positive. And so they get divided, so that's a positive. Let's plug in -1/2. We get a positive and a positive, which is a positive. Let's plug in +1/2. We get a negative and a positive, which is a negative. Let's plug in 2. We get a negative and a positive, which is a negative. Now, these open circles are important. Please include them. So let's talk about our increasing section. Our increasing goes from -infinity to -1. We got to skip that because that is not a critical number. It is a point that doesn't exist. It's an asymptote. And then we go from -1 to 0. And then we are decreasing from 0 to 1. And then we skip that point at 1, and then we go to infinity. That's why the open circles will help you, hopefully, to skip that point. Now, we do have a point that is a critical number because this point of 0 something happens. We are increasing to 0, and then we are decreasing. So we know that when x equals 0, we have a local minimum. Okay? Anytime you go increasing, decreasing, you'll have a minimum. Oh, I'm sorry. I drew it. That's a maximum. That's a peak, isn't it? Let me do it again. We're increasing to decreasing, that's a local max. If we go decreasing to increasing, it would be a local min. So we do have a local max at that spot. Okay. So let's see. So now we're done with our first derivative. Excuse me. And now let's go to our second derivative. Now our second derivative is what we used for part G, concave up, concave down, and inflection points. So now we are going to use our second derivative. So let me write this over here. You'll notice that we have that same x squared minus 1, except this time it's cubed. So if we put this in factored form, the top we could factor out a 4. The bottom we can factor that to be x plus 1 cubed and x minus 1 cubed. Okay? Now 3x plus 1 doesn't factor further, but let's just take a minute and solve it for, let's set it equal to 0 and solve it and see what happens. If we set 3x squared plus 1 equal to 0, because remember, critical numbers come from where the top equals 0 and the bottom equals 0. And if you just even take the first step here, you get 3x squared equals negative 1, which means that there are no real critical numbers. Because remember, that would give you like an I, that would give you an imaginary number, which isn't what we want. So this one has no critical numbers, no zeros. Of course, these have those same old plus or minus 1. So on our second derivative chart, the only thing we have is plus or minus 1, and they are open circles. Okay. But we need to include everything. So I'm just going to write down the top, and I'll write down the original. Well, let's actually split those. Let's give me one more row here. Okay, so I've included all the factors from the bottom. That's those two. Sorry, they're not in a great order. And then that's the factor from the top. Okay, let's plug in -2, 0, and 2. If we plug in -2 to the x minus 1, you get -3 cubed, which is a negative. In the middle, you get 13 times 4, which is a positive. And on the bottom, you get -1 cubed, which is a negative. And then 2 negatives multiply together to give us a positive. Now let's plug in 0. I get a negative, a positive, and a positive, which is a negative. So far we know that the left side here is concave up. This one is concave down. Now let's see what this one's doing. So if we plug in 2, we get a positive, and a positive, and a positive, which is a positive. So now let's summarize. So we are concave up from -infinity to -1, that first piece, and also from 1 to infinity. And then we're concave down in that middle section from -1 to +1. There are no points of inflection for this one because there are no points that are critical numbers. So you can't have a point of inflection if you don't have a point that is a critical number on your second derivative chart. So no inflection points for us. Okay, and so now we have to get an accurate graph. I think that's what I was trying to say with H, accurate graph. So let's now put all these pieces and parts together. Okay? So hopefully you got all that copied down. I'll give you a second. And then let's put all these parts together into a nice, lovely graph. So to graph it, the first thing I usually put on are the intercepts. So remember, we had a vertical, or no, I'm sorry, the asymptotes, and then I'll put on the intercepts. So we had a vertical asymptote at +1 and at -1. We had a horizontal asymptote at 2. Now, horizontal asymptotes only include the end behavior, so I do tend to just put them on the left and rightmost ends of my graph. Okay, so there you'll notice I put on the vertical asymptotes and the horizontal asymptotes. I do tend to almost follow kind of the order we did it in. The only intercept we had was at 0, 0. So far that's all we know. Now let's think of our first and second derivative chart. We know on our first derivative chart that in this section we are increasing. So it would make sense that this goes like that. And we are also concave up, and so my picture is concave up there. If we went here, we're decreasing and concave down, and we shouldn't be hitting this anyway. And then, so I'm assuming there's a piece here. Now, if you're unsure, that's where you plug in some darn points, and you can plug in as many points as you want. Let's plug in -2 and -3, and let's see if it's doing what I think it is. Now, remember, we're plotting or we're graphing the original function, and so when we graph the original function, that's where you want to plug it into. So let me write down the original right here so I have it to look at. This looks like a lovely, beautiful, colorful, scribbly mess. I'm so sorry, but anyway. So if you plug in -2, you get 8 on the top, and then 4 minus 1, you get 3 on the bottom. So 8/3 is 2 2/3. No, yeah. Yes, it is. It's 2 2/3. So over here at -2, we are up at 2 2/3. Something like that. Maybe not quite that. And then at -3, let's plug that in. We get 2 times 9, or 18 on top. We get 9 minus 1, or 8 on the bottom, which is 9/4, which is 2.25. So this was about 2.66, 2.7, and this is about 2.25. So we've come down a little bit, which makes sense, right? Because remember, this piece should be concave up and increasing. So that piece, we just focus on this and this from our plus and minus charts. Okay? Okay. Now let's do our middle piece. Now let's look at the middle piece. From this piece, we can see that it should be increasing and decreasing. And this piece tells us that it was concave down. So does it make sense? It looks like kind of an upside down parabola. So, I mean, if you put those pieces together, you should get something like this. If you are unsure, I don't know, plug in a point. Now, let's remember the symmetry. We should be able to fold this over the y-axis, and this piece should have a matching image over here. So we shouldn't have to plug in any points. We know that this is going to be 2.7 and this is going to be 2.25. And so guess what? What was that piece? It was decreasing. It was concave up. Decreasing, concave up. But what could you do if you wanted? Plug in 2, plug in 3. Guess what you're going to get? 2.7 and 2.25. So the symmetry can help you. The plus or minus charts can help you. And if all else fails, plug in some points. Remember, our domain, right off the bat, had 3 pieces of it. If your graph does not have 3 nice curved pieces that are just separated by asymptotes, you've done something incorrect. Okay, so that is number 3. So hopefully that is helping get all of this stuff in your brain. At least we can help, right?